Hello, welcome to the video. Today we're going to be discussing an interesting debugging technique for embedded systems that I've had the opportunity to put into practice recently. And it's funny because it's quite a simple technique, but I have the feeling that not too many people know about it or would use this idea as a debugging technique. So I want to share it with you because for me it was useful and it came in really useful recently. And so the idea is this actually gives us the ability to debug systems just using light. And that's pretty cool, right? That's a pretty interesting idea. So I want to narrow in on what that actually means. So in this situation, in my particular situation, I was dealing with a device that was completely sealed. And it was very difficult to interact with this device or interact with the board of the device and measure signals with, say, an oscilloscope or a logic analyzer or something like that. So I did have the ability to program the device and debug it using a step debugger, but I didn't have the ability to measure a signal, so be able to change a GPIO or observe a PWM frequency or any of that kind of stuff. So that was kind of a difficulty I was having there as I was bringing the system up. And, you know, the details of why the system was sealed are not that important. Sometimes this is a situation you're going to face. In this case, it was a valid reason that that was the case. But yeah, how do you actually go about figuring some stuff out in that situation? So I had a step debugger, and that helps. That helps for a lot of things. You can figure out logical problems that way. Something you can't really figure out is really detailed timing things. So if you are trying to, for example, do a process that takes 1 millisecond or 100 microseconds or something like that, and you really need to measure it to make sure it actually takes that amount of time, that was just kind of not possible with this device. But the device itself does have LEDs on it, right? There are user-facing LEDs for this device that allow you to see the status of the system, essentially. And of course, I'm writing the firmware for this, so I have control over those LEDs. So those LEDs can actually be an output mechanism that we can use to observe the state of the system in a much more detailed way than just regular is it on or is it off kind of way. Okay, so what I want to do is I want to show you some code that I've made for an Arduino here, which of course is not a sealed system, but it's going to act as our kind of test environment here to illustrate this concept. All right, so this is the Arduino code that I've got, and the idea is that we've done some setup. Right, there's a bunch of setup. This is a much more complicated system, of course, in real life. So there's some setup that's been done, and then we have a main loop down here. And of course, in the main loop, we're doing all different kinds of things. We're reading user input, we're measuring analog voltages, we're doing computations, and we're making outputs on the system, right? So maybe we're blinking LEDs, we're communicating with other chips, whatever. But somewhere in the middle here, there is a thing that takes approximately 17 milliseconds, right? Or rather, in this case, we know that it should take 17 milliseconds. Let's say exactly 17 milliseconds. But we can't measure that. There's no way for us to know that because we don't have access to like kind of the inner board. We can't actually probe that in a really precise way. So what do? Well, in this case, the idea is that we're going to basically blink the LED kind of before and after, or rather, you know, we could do it before and after in this system, but there's actually stuff that happened. There's nothing that really happens afterwards. So what we're going to do is every time we come to do something in this process, we're going to flip the LED from on to off or off to on. And then that's it. That's going to be our output. And of course, an LED blinking at 17 milliseconds, as it's detectable by the human eye, you probably can see that. If you look closely at it, you'll probably see it like just not going on and off, but you'll see a change in brightness. If you were to hold a camera up to that or something like that, if I was to even show on the screen what that would look like with a camera, I'm not going to be able to show you it because even a camera that runs at 60 frames per second is going to be basically extremely close to the frequency of the actual change that we're trying to observe. And because of that, we're going to alias, and we're not going to see that change in the frequency, because we can't observe a 17 millisecond signal on a 16 millisecond update rate, right? That's just not going to happen. So how are we going to solve this? All right, well, let me show you. You may already have some ideas, but this is going to be the key component. It's extremely cheap, and you probably already have it around if you've done some electronics. This is a light-dependent resistor. And what that means is it's a two-terminal device, and it's a resistor, but as light actually hits this, this sensor here, the amount of resistance that this resistor puts out changes. And basically that's going to be our mechanism for figuring out how that signal that we're trying to observe is actually changing. Okay, so let's go back to the code over here, and I'm going to open up a little diagram that I have. So this is just a voltage divider. This is what happens when you take an input, a power source, in this case 5 volts, and you pass it through 2 resistors in series, and then that goes off to ground or some other point. What's going to happen in this is that if you observe what's happening at the point between these 2 resistors, you're going to observe a voltage drop, right? And it's going to be somewhere between what went in and 0 volts down here on ground. Now, in the case that you have 2 equal resistors, what you should see is exactly half the voltage. Of course, like, you have to account for the fact that components aren't perfect, and you might not see exactly half. But yeah, you're going to see something very close to half the voltage that went in. And there's a formula here for how you actually calculate, like, kind of what you're going to see on the other side based on your 2 resistors. And the idea is that it's proportional. So the proportion of this resistor to this resistor is going to say kind of like the percentage that you're going to see on the output here. If we take that principle and we actually replace our 2 standard resistors with a light-dependent resistor on this side, that's my schematic here for light-dependent resistor, and a potentiometer, and that could also be a fixed resistor, but I've made it a potentiometer to have a little bit of adjustment, then what we can do is we can actually put a probe in the middle of these 2, and by a probe I mean like an oscilloscope probe. And we can actually observe the changing voltage here. And the reason the voltage is going to change is because we're going to hold this light-dependent resistor up against the LED that we're trying to observe, right? And if we're able to sort of do that effectively enough and try and remove some of the ambient light around in the room, what we're actually going to see on the probe is the resistance of this change, and therefore the actual voltage drop here is also going to change, and we're going to be able to observe that as a signal on the oscilloscope. And that's it. That's how this thing works. It's a really, really simple idea with really cheap components, and this is going to be how we're going to see that change that we can't actually get to. Now, again, I'm going to try and zoom in here. This is the device that I've actually built for this purpose. So as you can see, it's a potentiometer on a little bit of prototype board with 3 connections. So one of those is going to the voltage, one of them is going to ground, and the one in the middle there is the signal that we're going to observe with our oscilloscope probe. And on the other side, what we have is the connections and the light-dependent resistor in the middle there, right? So that's what we're actually going to hold over the LED and try to detect that change. All right, so that's it. It's so simple, it's stupid actually, but it really works to within some degree, and we'll talk about the limitations of this shortly. But this is what we're going to have. So before we get into that, we need to write the code to actually observe this. Turns out it's really simple. So what we'll do is we'll add a variable up top called LED on. We'll set it to false in the beginning, and then every time we're going to come to observe this process, we're going to set LED LED on to be whatever, like just a flipped version of that previous. So it will go from true to false, false to true. Then we can say if the LED is on, then we're going to write to the LED port the LED pin. And if it's not, then we're going to do the opposite. We're going to turn off the LED pin. So we do this like, why can I not get, yeah, okay. And you might be wondering why we're not actually using the built-in Arduino functions here, like digital write and digital read. Just digital write in this case. Well, the reason is that digital write actually does more than just turn the pin on and off, right? It does a bunch of stuff under the hood to try and regulate the Arduino's internal timing, to try to normalize the pin definition name that you give, like pin 13, digital pin 13 or something. It needs to translate that into something else. So there is a bunch of extra work that the Arduino framework does, and that might interfere with our timing. And I want to have as little influence on the timing of the system as possible. So what we do here is we do one variable write, so one write to RAM, and we have a conditional branching statement, and we are doing a peripheral write to memory. So it's just a couple of operations. It's the minimal amount that you can do for this. So that's what we're doing here. Okay. So what's going to happen here is every time we come into this loop, we're going to do this process. We're going to do the thing. And of course, we don't actually do anything afterwards. So we are immediately going to come back here, flip the LED off or on, and do the thing again. So what we're going to see is we're going to see every time that this changes from low to high, or the LED on to the LED off, we're going to have done this process one time. So if we can observe that change between high and low, we can determine how long this process actually took. Did it take 17 milliseconds? All right, so let's actually verify this code. And it's good. And then we can upload it. So I'm uploading it to the Uno I have sitting on my desk. And now that is running away. And I can just about see the light flickering. I think if I raise this up to the camera for you, you probably won't even be able to see a detectable change in the LED. It's this LED next to the orange Captain tape here. No, I think you can't actually observe that on video. It doesn't look like it's even blinking. I can actually see that it is flickering here, but because of the aliasing of the camera, you won't see it here. Okay, so we have that code running. And what I'm going to do is to use my Digilent Analog Discovery, the Analog Discovery 2, which is a kind of multi-tool, like an entire workbench in a single device, right? It's got a power supply, it's got a waveform generator, it's got an oscilloscope, it's got a logic analyzer. It's kind of got everything that you need in the smallest possible amount of space. This isn't sponsored by Digilent. I do really like this device and I use it quite a lot, but they're not sponsoring this, so don't take this as as some sort of advertising thing here. We're going to zip over to the waveform software, which is kind of the software that runs this thing, and we can open up the power supply part here, so I can actually supply 5 volts to the device, and we can open up not the waveform generator, the oscilloscope. Okay, so that's running here. It's not actually running yet. Now I'm going to plug in the device, and so what I'm going to do is turn on the power supply and turn on the scope. And hopefully when that starts kicking in, what you can see is that we've got a changing voltage level here. And basically what I'm doing now is I'm just holding my hand over the LDR and raising it off, and you can see that we see the voltage changing. So as this thing gets more light, the resistance goes down because we have almost 5 volts on the signal. And as I stick my hand over it and cover the light, the resistance goes up and we get a bigger voltage drop. Okay, so let's see if when we hold this thing over the light, the LED, do we actually get a change? And what you can see here is that we get a very observable signal. And I'm just going to stop it there so I don't have to hold this with my hand. And I'm going to take a measurement. And the measurement I'm going to take is going to be between this low point here and the high point up here. So let's stick the first one down here, and we'll go to the high point. And what you can see is that the delta X here is 17.05 milliseconds. So that's it. We've actually observed the timing of this thing. We can say concretely, okay, this thing takes 17 milliseconds. Great. And we didn't actually have to put a single probe on the board. In fact, we couldn't. We could only observe the LED. So this is kind of interesting and cool for a number of reasons. Like, one very obvious one, and this is kind of incidental but also kind of nice, is that these two circuits are completely isolated from each other, right? So the power supply and the oscilloscope and everything is completely disconnected from the circuit we're trying to observe. So that's kind of just an interesting thing. This is a passive way of reading the signal. We don't have to invasively get in there and try and, try and actually physically probe the board. The other thing that you might notice is that this is not a nice clean square wave. It looks like a capacitive kind of effect here. So like there is a, it takes time for it actually to get up to the level. And I think that's a couple of things going on there. I think there might actually be a capacitive effect from the board itself next to the LED. I haven't actually looked at the schematic here, but I think there's something going on there. And of course there's another part, which is that the LDR, the light dependent resistor, doesn't respond extremely quickly. So it has a rise and a fall time, which is counted in fractions of a millisecond. So what we can see there is that, yeah, that's going to take some time, but this is actually working really nicely. What we might want to do is to run this again, and I'm going to put the probe back and see if I can do this at the same time. So I'm going to try and zoom in a bit, as much as we possibly can. And I'm going to try and stop here and try and take a slightly more accurate measurement of what we have. So I see here that this is the peak, and it's going to begin to drop down here. And this is the absolute low point. And what we can see is then we get really close, 16.99 milliseconds. And we're well within the realm of this being kind of just not being able to get close enough to the signal and measure it on the exact points. I think here this is pretty clear. We're hitting that target. So this is great. This is the whole technique. One more thing to note. So I'll run the scope again, and I'll put the probe back. I'm getting the LDR. I'm getting it as close as I possibly can to the board. And I think what you should be able to see is that the actual kind of bandwidth of this signal, the amount of like data that we're actually getting for what we have here is not that high. So the high point here is at maybe just under 4.5 volts, and the low point, or rather we could actually measure this. So we have this point here, and we have this point here, and so the difference here is 1.12 volts. So we have a 5 volt range, right? We're putting 5 volts through the voltage divider, and we only actually have 1.21 volts of change that we can use to observe this. So the tricky thing about that is that we can't plug this into a microcontroller and expect to read this signal, at least not in a digital way where we could expect to see these as digital peaks, because we're actually just not going to detect the difference between the levels here. Something we could do is to process this signal a little bit. So try to remove this offset, so you can see that the signal kind of begins and ends all the way up here at kind of 3 point something volts. We could pass that through a capacitor and recenter that on 0 or reground that, and then amplify the signal that we have, and that way we could actually use it. But that's going to take some more components, and it's going to be a little bit more involved as a kind of device to get set up. But that would work as well. But in general, this is actually a really useful technique. I think it's a really interesting one. And yeah, it actually works pretty well. We get a good signal out of this thing that can be very easily probed on the screen. If you wanted to improve this technique, one thing you could do is to use a photodiode instead of a light-dependent resistor. And a photodiode is, it's basically like a tiny little diode that also has this photovoltaic effect. So, photons on it change how current flows through the diode. And you can do the exact same thing where you basically build a circuit where you will be able to detect changes in light based on how much light is hitting the photodiode. And the nice thing about a photodiode is it responds much faster. Like you can see really microsecond level changes using a photodiode. The difficult part about it is that you need to have a much more involved circuit that involves a transistor in order to amplify the circuit. It's a little bit less intuitive how that actually works, but it is doable, and there are schematics online and you can build it. And it is a great way. If you've got something that you need to measure that's going to be down in the microseconds, this is going to work way better. All right, so that's kind of it. I just wanted to share this technique with you. Before we go, you might be wondering, what is this thing that takes approximately 17 milliseconds? Like, how am I doing this? Well, it's just a delay of 17 milliseconds. So it's not very exciting, but that is the process. This, of course, is standing in for any complex behavior we have. And something, for instance, that we might have is firing an interrupt at a very fixed frequency, right? We might be wanting to take an interrupt every millisecond or something like that, and we want to know how accurate that actually is. This is one way we could do that. Okay, so last point is that I try my best, and I do in fact on all videos on this channel, I just turn off all the advertising, so I don't make a single penny from YouTube for these videos. And of course I'm not trying to make money from these videos, but I do have a Patreon. And you can choose to support there with any amount that you choose, if you have the means and the ability, and if these videos are useful to you. It's kind of nice. It helps me to just buy equipment and things like that I can use on the channel. It gives me a little bit of an excuse to be able to do that. So that really helps. And one thing I'm going to start doing more now is to post videos that accompany the main video on the Patreon only, and there'll be a little bit behind the scenes and a little bit more information, maybe a little bit more depth about the main topic. So if that's something you're interested in, or you just want to support the channel, please feel free to check out the Patreon. You'll find a link in the description. But if you can't, then just tell someone else about these videos. I'd also really appreciate that. All right. Thanks very much. I hope you enjoyed this. I'll see you next time.